I want to address number 2 and 2 ways you could solve this problem. One way you could look at it is how I posted on my Edmodo keyword. Consider any of these values outliers because they aren't that different from other values in the sample. And if you look at the histogram of the data, so I'm going to look at the histogram of my data, zoom 9, I see that it's unimodal, fairly symmetric, okay, unimodal and fairly symmetric. So I think, okay, this is normal enough that we can assume normality for our t-distribution. However, if you go to the box and whisker plot that shows us outliers, now I have a different point of view. I have an outlier in the upper end and the lower end of our range, okay? So what you should do is remove those outliers. I believe that the AP Stat, if this was an FRQ, the graders would count either one correctly, like you can still get an essentially correct, as long as you support your answer with statistical language that is accurate. Okay, so let's look how to do that as if we removed our outliers. So I'm going to remove 40 and remove 21 from my data. So state what we want to know. We want to know if scientists should be concerned that babies are taking longer to become potty trained. We make our plan. A random sample of 15 babies. It is safe to assume 15 is less than or equal to 10% of all babies in the U.S. So independence is met. These first 2 things show that we have independence in our sample. 3, the sample is not large enough to use the central limit theorem. It's not greater than or equal to 30. We also don't know if the population data is normal. So we can't say, well, if the population's normal, the sampling distribution is normal. But what we can do, the third scenario, is to look at the sample distribution. So look at the distribution up here, which we already did. And I noted that it is unimodal and roughly symmetric. That wiggle word's important. It's roughly symmetric. But there are outliers, 21 and 40. So we remove them and proceed. Guys, I recalculated my 1var stats with only 13 data points. I went into I took out 21 and I took out 40. And I said, with conditions met, we can construct a 95% one sample mean t-interval. We're using a t-distribution. We do not know sigma. We have to use a t-model. T-interval with degrees of freedom of 12. X bar is 30.846. That's my new sample mean with the outliers removed. And my standard deviation is 3.937. Guys, this is the biggest difference. If you don't remove those outliers, your standard deviation is over 5. So now we have a very of over 5 instead of just shy of 4. That's a pretty big difference. We construct our confidence interval, statistic, plus or minus the margin of error, your critical value, which is a t-star, times the standard error of the mean. All the values, 30.846 plus or minus my t-star, which I can get from the table or from the chart, times my standard error of the mean, and this is my interval. Scientists should be concerned because 26 months is not in our 95% confidence interval. If you wrote up the conclusion for this interval, you would say we are 95% confident that the true mean for average time it takes babies to become potty trained is between 28.45 months, don't forget your units, and 33.22 months. Now, on part B, it asks us to interpret confidence level. 90 means in several random samples of 50s, 95% of the intervals produced will have the true average, or will capture the true average potty training age. And then the last part of this question asks you to solve for n. I just want to make a point that if you're given margin of error, you have to take your critical value times your standard deviation of z. Guys, the problem is We can't find T star if we don't know N. Okay? If you don't know N, then you can't calculate degrees of freedom. If you can't calculate degrees of freedom, then you can't find T star. So instead of using T star, we're going to go ahead and use Z star. And you want to make sure that you always round up.